Okay, welcome to today's lab. It is lab 11, rotational motion for physics 220. And today's lab deals with the idea of rotational kinetic energy. So before, when we've talked about kinetic energy, we've talked about translational kinetic energy. And that is literally the energy of moving from one point to another. But rotational kinetic energy is the energy of actually rotating. So you can't just rotate an object for free. It takes energy to rotate an object. So when you start with an amount of potential energy, some of that energy is going to have to go into rotating the object. And so if you paid attention at all to the pre-lab, it asks you about rolling without slipping. And what that means is the object's as the object rotates, so if you have a circular object and you start rolling here, and this is 2 pi r, it's going to make one complete rotation to travel this 2 pi r and get back to this point. So one complete rotation means that you've traveled one complete circumference. If it slipped, it wouldn't stay rotating on the surface. It would slide a little bit, and so you would actually travel further than one circumference. You would end up traveling 2 pi r plus however much you slipped. So only in the case where your object isn't slipping does your distance traveled equal 2 pi r or theta r. So if theta is your rotational distance, theta r would be your linear distance. And so only in this case is velocity equal to omega r. And so this brings me to rotational motion, has analogs similar to linear motion. So for a given distance traveled, you have your rotational equivalent, which is theta. And theta r is equal to linear distance. Similarly, you have velocity, which is corresponding to omega, which looks like a W. And omega r for non-slipping is equal to v. And then it's not super important for this lab, but there's also an acceleration analog, which is alpha. And similarly, alpha r is equal to a. And then for mass, there is a rotational analog, and it is inertia. And it is actually equal to some fraction based on the geometry of your shape times m times r squared is equal to I. And I just realized I did those backwards, but it's going to be okay. And so for today's lab, what we want you to do in the beginning is calculate the total energy of an object and to figure out its final speed. And so I won't go through all of it with you, but the main point we want to get across is instead of saying mg h initial plus 1/2 mv initial squared is equal to mg h final plus 1/2 m vf squared, we're now going to have a rotational component to our kinetic energy. And so instead of just being this equation, we're actually going to have mg h initial plus 1/2 m v initial squared plus 1/2 I omega initial squared equals mg h final plus 1/2 m vf squared plus 1/2 I omega f squared. So it's these two components that are your rotational kinetic energy. And so as you can see, some of the energy from potential energy is going to end up going into rotating the object, not just moving the object down the ramp. And so just to go a step further, we know initially our object is going to be at rest, so it's not rotating or moving. And so we just have mgh initial. It is going to end at some height with some velocity and some rotational velocity. And so we're going to end up with mgh h initial minus mgh final is equal to our total kinetic energy, which is 1/2 m vf squared plus 1/2 I omega f squared. And so we can write this a little bit further. We'll get mg hi minus hf, or delta h if you want, is equal to 1/2 m vf squared. And then from above, we can see that omega r is equal to v, or omega is equal to v over r. And so for this, we'll get 1/2 times some fraction, which is given in your lab, m r squared times vf over r quantity squared. And so your r's will cancel and you'll get left with something m vf squared, and so your units are going to check out. And that is how we want you to go about solving for the final equations, the final velocities of your rotating objects. So now to get to the mechanics of the actual lab, as I adjust this camera some so you can hopefully see what is going on. And so we have this ramp with some initial h and some final h, which I will give you. And then we have our three objects. We have a cylinder, or a sphere, which is just a ball bearing. We have a cylinder, which is an aluminum rod. And then we have a copper pipe fitting as our hoop. And so again, these three moments of inertia are given in your lab. And we will be rolling these down the ramp to see which one gets there first, and then compare that to the prediction you'll make based on the final velocities you calculate. And then I will also take data, rolling them individually, so you can calculate a final speed and compare that to the final speed you've calculated. So